All right, I love that so many people came to see a presentation about database internals. Not too many people are interested into this topic, but really happy to have you guys. So, details about me: I'm currently working as a database environment engineer at CrateDB, and what I do and my team does, we do drivers, connectors, integration, documentations, and sometimes we go into conferences and try to talk about CrateDB. So nowadays, there are a lot of databases, right? Is there anyone using a database? Can you raise your hand? All right, everyone is using a database, right? There are so many different databases, and I'm even missing quite a lot. I didn't really put vector databases. I'm missing key value databases, graph databases, Apache Pinot, Star Tree. I'm missing many databases, and the reason why there are so many databases is because they are fundamentally one of the most complex pieces of software that you can probably develop. And that's because there are so many internal components that you can optimize for so many different use cases that naturally you end up with a lot of solutions for so many different problems. But there are many techniques that we use at databases, and one technique that pretty much everyone does is indexing data. So, and that's something that we're going to be focusing a little bit about in this talk. How do we ingest data, how do we index, and what is it that we do at CrateDB? But first, let's ask the question of why do we index data? So imagine that we have this array of data. At position 0, we have the value 5, position 1, 3, position 20, position 2, we have the value 20. What if I want to get all the positions of the value number 3? What would you do? Any ideas? You will iterate through the values, right? But that has a problem. Does anyone know about the problem? The problem is that the bigger the array becomes, the more operations you have to make, because the complexity of this is, this is the code that they could write. I just iterate through every single value. If the value is the one that you want, you return the position. Now you have all the positions. Now this has a problem. As I said, the complexity is O of n, and the bigger the table becomes, the slower it is. So it is not too efficient. So what would we do to make this faster? It is not a trick question. It's on the title. We index things, right? So the first thing that we could do is we change the data structure. Before we had an array, and now we have, in this case, a hash map or a dictionary in Python. Now, instead of having flat values, we map the value, with the position of the array. This makes everything way faster, because now we just need to access whatever value that we want, and we get the positions. Imagine that the positions are the offset or where your actual rows are stored in disk. That would mean that you would now be able to get the data back to your database way faster. And it depends on the implementation details of the hash map, but typically it's O of 1, right? So the general story about indexes is that we trade storage and write performance, because now you need to create this new data structure, and you need to get the data in. If you update values or delete, you need to do stuff. We trade that for faster queries. These are some simple, some very common index structures. For example, there is the inverted index that we often use in full text search, bitmap, which is amazing for low cardinality values like true or false, sex, age. And then there is the B-tree index that we use the data structure for B-trees and B+trees. And this is probably one of the most used index across all databases. It's very, if you have a data type that you can compare it to, you can just index with a B-tree. And yeah, so there are caveats. It's not, you cannot just start indexing your values like nothing. Indexes depend on the implementation details. Every data structure has very wide implementation details, and you can implement the same data structures in many different ways, right? And that creates a big cognitive overload if you are trying to speed up your queries. Not so long ago, last year here in CrateDB's, there was a talk where one guy was optimizing its indexes for full text search, and it was a really long talk, and he needed a team of 6 to make his search faster. So it also you need databases experts. You overall increase the cost. And this is more for implementation details that depend on the system, but you typically need to reorganize the indexes. As your data grows, the statistics of your data will change, and your index will probably start being less effective. So you might need to change the data structure, or you might need to tweak things differently. So now the actual core of the talk. What is it that we do at CrateDB? CrateDB, we fundamentally change how we do things, typically do things with indexes. We index everything by default. Every single column, we index it. We can do that because our storage level is based on the Apache Lucene framework. And we not only index every column, but we also build a columnar and row storage. So what does that mean? That means that every time I insert a value, for example, here we have metrics, every single value gets indexed. We leverage the doc value data structure from Lucene, which is the columnar store, and depending on the data type, we use one index or another, obviously for its efficiency. For text, we use an inverted index, block KD3 for numerical, geospatial, and dates. Full text search, we use a full text index. We use different analyzers, and from vectors, we use HNSW graphs. And when it means that we index everything, I actually mean that we index everything. For example, here we are inserting one JSON object. We are also indexing the columns. And you can have arbitrarily deep, nested deep JSON objects. You obviously, it is not unlimited. You obviously at some point run out of memory. But yeah, you can just, it can be as deep as you want. So what does that mean for you as a possible CrateDB user? That means that you just need to create one table. This is the table definition for the insert that we saw before. Out of the box, the data is indexed. You have fast queries, and you don't have to worry about reorganizing the data, into which column do you build the index to. It's just all by default. So we completely change the way we think about indexes. Now, obviously, I told you about many. I also told you about some indexing caveats. One caveat is that we trade storage for faster speed. So obviously, there is always going to be some kind of something that you have to pay for the indexes. This is an example of a 45 megabyte Parquet file, which is the New York taxi one. And as you can see, the original one is 48 megabytes. And in CrateDB, it only takes 260 megabits, which is very cool because we are even taking less space as MongoDB, than QuestDB, and than Postgres. So as you can see, there is some overhead, but we're very optimized, so it is not too big. Still, if you know that in your queries, some columns will never be used to when you are querying, when you're doing joins, when you're doing word statements, you can actually disable many of these things. For example, you can set index off, you can set the column store to false, and you can also change the codec algorithm. This is also, this is exactly the same data set, and what I did is I did a very different combinations of turning things on and off and see what the actual effect of the indexing affected the storage. And we can see that the index was only 13%, column store was very similar, 13%, and the codec was 26%. So amazingly, we don't really take too much data. Typically, when you build index, you don't always depends on the data structure, but you always usually build the index with less data. You don't really need a full copy of the data, but sometimes, it depends on the type of index. And also, we need to pay some kind of overhead when we are inserting, updating, and deleting values, right? But there is some fundamental aspect of CrateDB that allow us to be very efficient about it. Tables in CrateDB, they are split in shards. always splitting shards. Well, you can have only one shard, obviously, but typically you build several shards. Every shard is mapped on a one-to-one of a Lucene shard, of a Lucene index. And every Lucene index, it's further split in segments. And segments, they can be split, they can be searched independently. So every time we make an insert, we can build a new segment, just append it. We mark the old segments or the documents are as not valid, so then we can just skip those segments, so we can get data in and pay less overhead performance. Obviously, if you are constantly writing new values, you're gonna end up with a lot of segments, and we merge those asynchronously behind the scene. There is a merge policy, and depending on some conditions, we merge the segments. You can also do that manually. There is some command that we call optimize, and you can also define the number of segments. But typically, you will let CrateDB handle that for you. So you do not need to take care of how the indexes are built, how they are optimized. CrateDB does all of that for you. So every time we insert a new record, two things happen. First, we commit it to the translog. A translog is it's a transactional log. So if you're come from Postgres, they call it a write-ahead log. So if your node goes down, we can replay the operations and you don't lose data, which is great. And we commit it also to a memory buffer. Every second, if there was a search operation, every 30 seconds, we call internally a refresh operation, and we build a new memory segment. So the data is still not in disk, it's on memory. But the moment the segment is in memory, the index reader, they are bounded to the segment that they were created from. So we update that reference, so now the data is available for search. That means, a small caveat, is that whenever you insert data, there will always be a small sub-second up until a second of overhead where your data will not be available. Then at some point, Lucene will flash it, which means that they will put it into actual disk, and then we'll have a new segment. And as I said before, we have merge policy, so at some point it will merge. We'll have a bigger segment, and oftentimes that will mean that we'll also take less storage. So the idea is that you are constantly getting more data in, more segments are created. It's an append only thing, so we don't really have to stop any process. You can just keep getting data in. We merge it, we optimize things for you, and that's great. So how do we fare against other databases? Last year, we paid for some external benchmarking, and we compared to MongoDB and to InfluxDB. So this is CrateDB without any optimizations, because you can always further optimize for your use case, right? And we are running the TSBS, which is the time series benchmark series. We can see that at first, we just beat MongoDB really fast. But if in MongoDB, it seems like if you optimize further and you properly index two columns that are very used in the queries, they beat us. But there is something very funny that happens. Without doing anything, queries are sub-second, but you have to actually take manpower and further optimize the database in order to beat us. And you can see that the more complex the query becomes, the slower MongoDB becomes, but CrateDB still sounds very strong. So that's great. Get your data in, everything's fast, forget about it, and focus on building a product. And the next one, this one is really, even more interesting in my opinion. This is InfluxDB. Well, something I didn't mention is that CrateDB is heavily optimized for read operations. So we are almost never going to be faster than the databases that optimize for write speed, but still we are very good at inserted rows. You can see that we did 180K rows, 180K rows per second, while MongoDB was only able to get almost to one up until 100. I guess InfluxDB is a different story. We keep the rows per second; they're still slower than us, but they are very fast. InfluxDB, it's a time series database, so it's very optimized for time series. But the same thing happens with MongoDB. simple queries, they perform well. But as they get more complex, you can see how at some point, we almost get into the same range until InfluxDB dies. But your CrateDB still returns. So it might be slower on the simple ones, but we still return. Now, CrateDB is an open source database. We are licensed under Apache 2.0. So if you want to have a look at us, you can just check us at github.com/crate. We are very friendly to open source. And also something that happens in CrateDB is that we get sometimes we get a lot of people contributing, which is not necessarily something that happens in other databases, because database internals are very complex, but we actually get, oftentimes we get a lot of people. We have a Docker image. You can just Docker pull the crate image, or you can try our cloud for free. We have a really friendly, we give you too much data. We give you, the machine that we give you to try out for free, it's too good. So you can take advantage of that if you want to try things out. And it seems that I still have some minutes left. This is the extra slide in case I was talking too fast. I said before that we are very optimized for read operations, and that also holds true when we talk about the actual infrastructure of CrateDB. We are a distributed database, and we have a share nothing architecture, which means that every node that you put up of CrateDB has everything to work on itself. If they can communicate, they will form a cluster, or they will elect a master. And that's amazing, because every time you make a query, you make a join, we can split that work into different nodes. And obviously, the more nodes you have, the more you will be able to handle. In the end, you will be having more CPU responding to those nodes. So yeah, this is the basic, the anatomic of a CrateDB node. We have the Lucene storage that we talk about a lot, the distributed execution engine, the planner optimizer, analyzer, parser, and then the protocol. We have a Postgres wire protocol, which means that you can use almost any Postgres tool and try and connect to us, or we have an HTTP endpoint that you can use. And yeah, that's it for me, guys.